This is a revision series for analog circuit subject, and in this revision series we will have 3 sessions. Okay, in the first session we will look at the approach to study this subject and the important points you have to remember for exam. In the other 2 sessions we will look at some problem solving. Okay, so if some student is a beginner and he wants to study this subject in less amount of time, so what should be the approach to study this subject? Okay, so let us see. And as you all know, for GATE exam, for EC students and EEE, this is a very important subject. You get around 8 to 10 marks. And for EEE students, from 6 to 8 marks you can expect. Fine. So what is the approach to study analog, right? Approach to study analog. Approach to study analog. So now in analog we deal with devices like the diode, BJT, MOSFET. So you will deal with devices like resistors, capacitor, inductor, diode, BJT, MOSFET, op amp, Zener diode. Okay. So how do we start? Whenever you want to start the subject, you have to remember that the first thing is you should define something called the current flowing through each device. Okay, so you have to define something called, or you have to allot a unique value of current to every device. For example, if there is a resistor, you can say there is a current I or I1. For a diode, there is some I1 or ID. And in a BJT, you have 3 terminals. So you can define something called I1 or IB, I2, IC, IE. In a MOSFET, you have IG, and mostly IG is 0. So you have ID and IS. If IG is 0, ID is same as IS. So, so you can define, you can allot a unique value of current to every device. And then you can allot a unique value of voltage to every device. Right? So the voltage across a resistor V here, so you can have VD here. So you can have VB, VC. So you can have VGS. This is the gate terminal, source, drain. So this is VDS. So you can have V1, V2, V0 like this. You can have some V or VZ. So you can allot a unique value of voltage and a unique value of current. And by allotting a unique value of current, the good thing about this is you will neglect the interaction that is happening inside the device. So that is the beauty in when it comes to EDC. When it comes to EDC or electromagnetics, now we are making a leap from these subjects to network, analog and digital. So in electromagnetics and EDC, you talk about the interactions inside the device. So here, even if you have a BJT or a MOSFET or even hundreds of BJTs or millions of transistors, the effort that you put for this simple network is the same effort you put for millions of transistors, right? So it will be surprising, but at this node, if at all you want to apply KCL, since you have allotted a unique value of current, so what is KCL? The currents entering is equal to the current leaving. Okay, right? So this law is called the KCL. So when you allot a unique value of current, then you can apply a law called the KCL law, right? Now this dot, if I can make it little big, right? So this dot, I'm making it slightly bigger here. Nothing changes. You can see here, this is I1 and this is I2 and this is I3. And what happens if just a moment. This eraser. Oh yeah. Now, what happens if I make this node a little big here and I stuff something like a BJT here inside, right? So this becomes the base current, this becomes the collector current, and this is the emitter current. So can you see? So the effort in analog is extremely simple when you compare with EDC. In EDC or electromagnetics, you talk about the interactions inside. But in analog, the effort that you put for the node and the effort that you put for the BJT both are same, right? So you in the exam, the examiner can give you a Darlington pair, something like this. Okay, so forget about what this is, but still you can treat this as a node or a black box like this, right? So the effort that you put here and the effort that you put here is same. So here you can take I1 and I2, or you can just be I3, right? So that is the beauty here. The defining current is not a simple thing, because when you define current, you're allotting a unique value of current at a branch, and if you can choose the element boundaries very carefully, then you can neglect a lot of things. You can neglect. So what are the things that you neglect? In electromagnetics, you talk about the interaction inside, which is the dq by dt, right? So we treat the whole thing as a black box, and forget about two transistors. You can take a digital board for that matter. So you can have a 1 million BJTs inside, right? So there are a million BJTs inside, and you have chosen the whole digital board or the analog board as a black box, and this becomes the current entering, and this becomes the current leaving, and the KCL holds good. So it's very important that when the student sees a problem, how much boundary he has to set up for that circuit. That is very important. If you choose the element boundaries so carefully, the effort that you put for this simple network is the same effort that you put for a million transistors. So next time you see a BJT or a MOSFET, or an op amp, just put a circle to that, right? And say that, I don't care the interactions inside. I'm just treating this device as a black box, right? So that is the beauty of this term called the current. The next term is the voltage. Now, how do you define a voltage at every port? To define a voltage, when you jump from electromagnetics to analog, you're actually doing d phi by dt 0. So what is d phi by dt 0? You don't want to know the interaction outside the device. See, in EDC, you're breaking your head to know the effect inside and the effect outside. Now, analog says that I don't care. I don't care the interaction outside the device, and I don't care the interaction inside the device, because I'm going to treat in analog all the devices as lumped elements or black box. So if you give me an op amp, which has a million, or which has, say, 10 or 15 transistors inside, you're just putting a circle and say that, I don't want to know what's there inside, because I'm going to treat this device as what box? A black box. And I'm going to allot a unique value of current and a unique value of voltage. That is the first approach. The second thing what you do is, don't think what is happening inside, don't think what is happening outside, just worry only about characteristics. Just worry only about what? Characteristics. The relationship between the node voltages and the relationship between the branch currents, right? So if you have a single BJT, the effort that you put for this BJT and the effort that you put for a million transistors, right? 1 million BJTs here is same. What is the effort here? Here you can take this as V1. Suppose this is base emitter collector. So you can take this as VB, you can take this as VCB, you can take this as VC, and you can go clockwise or anti-clockwise. You can go clockwise or anti-clockwise. If you have a million BJTs, so you can have V1 here, so you can have V2 here, so you can have V3 here, right? So you can go clockwise or anti-clockwise, the answer is not going to change. So you can say minus VB minus VCB plus VC equal to 0. So you can go like this for a million transistors, and you can say minus V1 plus V2 plus V3 is 0. Minus V1 plus V2 plus V3 is 0. So what I wanted to tell you is, the approach in analog is very, very simple, and analog doesn't care if you're strictly a good analog engineer. When you're solving problems, you will never care about you might talk about the interaction inside, interaction out, but while solving a gate problem, that is what I'm saying. What is the approach for somebody who wants to start the subject and finish it in a very, very small amount of time? He doesn't have to talk about the interaction inside. He doesn't have to talk about the interaction outside, because Kirchhoff will take care. The day you are applying KVL, you are neglecting the interaction outside. The day you are applying KCL, you are neglecting the interaction inside, and you are worrying only about what? Characteristics. From the characteristics, you will get an equivalent circuit or model. If it's a BJT, we will say that, if it's suppose a diode, we say, just don't care what a diode is, it's just a switch. Go and solve a gate problem. If you know the equivalent model, replace the diode by its equivalent model, which is a switch, and start solving problem. You can do clippers, clampers, peak detectors, voltage multipliers, and so on, right? And then apply what? The workhorse of the analog and digital world is KVL and KCL. KVL and KCL. So you have to apply Ohm's law, KVL and KCL. This is more than enough. So what are the tools that are needed for solving analog problems is Ohm's law, KVL and KCL. And of course, basic 10 standard coordinate geometry is needed, right? If suppose you are asked to draw the characteristics, you should at least know that if a line passes through the origin, it's y equal to mx, or if there are two parallel lines, the slopes are same, y equal to mx plus c and so on. So these basic coordinate geometry rules are needed if the examiner wants you to draw some transfer characteristics, and right. Okay, so once again I repeat, anybody who wants to start analog, whenever a device is given, neglect the interaction inside, neglect the interaction outside, and even the time scale of any input signal that you apply, input signal is always greater than the propagation delay. So this is another beauty, propagation delay. So what do you mean by that? So what do you mean by that? So it means that whenever I am giving an input signal to a BJT or a MOSFET, instantly output is available. Don't think about the delay. Unless and until the examiner gives you some parasitic elements or something like that. But otherwise, you give an input, instantly there is an output. You give an input to a resistor, instantly there is. So we are not worried about charge, we are not worried about the flux, we are not worried about the time. We are worried only about two things. One is the voltage. One is the voltage and the other one is the current, right? Okay, so this is the approach. Like I said, you have to define current, voltage, characteristics, equivalent circuit. So now I am going to give you the equivalent models for all these devices, which you have to remember for exam, right? Only the model. And anytime you see a device, replace that device with that model and try to solve problems. So solving problems we will do in the next session, right? So fine, and so three things here. Whenever you see a device, right, don't worry, at least while solving a problem, don't think about the interaction inside the device. That's an abstraction. Don't think about the interaction outside the device, and don't think about the time scale, right? Input is there, output, just go and solve the problem, right? Now, why this dq by dt has to be 0? So let me give you a small insight. Suppose you have a diode, or say you have a bulb. Okay, so suppose you have a light bulb. Okay, now when a bulb is given, how do we go with the approach? The same approach you have to continue for diode, BJTs and MOSFETs, right? In a bulb is given, you will neglect the interaction inside. Maybe there is a tungsten filament inside, you heat it to a certain temperature and all that. But you will allot a unique value of current flowing through the bulb, and you will allot a unique value of voltage, right? And then you will go with the characteristics. Now somebody has given you the characteristics of the bulb, which is say a straight line, So if you give 2 volt, the current is say 0.02. If you give say 3 volt, the current is 0.03. So something like this, okay? So this is the first step. This is the second step. The third step is the model. So how do you draw the model for this? The model for this is a line passing through the origin, y equal to mx, So V by I is 1 by slope, and the slope is change of y by change of x, which is going to be 100. And this bulb equivalent is a resistance. So at least in my class, in analog class, the bulbs are treated as resistors. Okay. So with this equivalent circuit, which is a resistor, you will solve the analog problems. The same approach you have to have for diode, right? So the diode characteristics, equivalent model, just apply, and after that you can apply what? KVL, KCL and Ohm's law. The last thing is you apply these laws and solve it, right? So the same approach you have to have for BJT. And what are the things we are neglecting actually? This is very important. Why we should not go inside the bulb? If you go inside the bulb, what happens is there will be an entering current, there is a leaving current, and the entering current minus leaving current will be charge buildup. It's so messy inside. If you go inside the bulb, then you have to choose the element boundaries very carefully and treat this whole device as one box. If you take the leaving current here, this is the entering, this is the leaving, then you can make dq by dt as 0. Then all the currents entering will become the current leaving, and it is just as a simple wire, right? So here the current is entering, here the current is leaving. All the entering currents is leaving. In between you can put whatever element, lumped element you want. You can put a resistor here, you can put a bulb, you can put a diode, you can put whatever you want, right? So that is, so don't talk about the interaction inside, don't talk about the interaction outside, worry only about current and voltage in an analog problem, right? Define voltage and current for a device, from the characteristics, prepare a model and solve, right? So because even if you want to talk about the interaction inside, for one device you will talk. Suppose the examiner gives 3 devices. For every device, thinking about the interaction inside is a waste of time. Say for example, I am having 3 bulbs. 3 bulbs. This is bulb 1, bulb 2 and bulb 3. And the VI characteristics of this bulb has a slope of say 1 by 10. The VI characteristics of this bulb has a different slope, say 1 by 20. The VI characteristics of this bulb has a different slope, say 1 by 40, right? Now what happens if somebody connected bulb 1, bulb 2 here, bulb 3, this is B1, B2 and B3. And what is the current I? If at all you want to find the current I, how will you do that? So each bulb is replaced by whom? Its equivalent model. And then you have to solve. Say for example, this is 5. This is B1 is 1 by 10, which is 10 ohms, 20 ohms and 40 ohms. Okay. So what is the current? This is, these two are in parallel. The combination is in series. So you're making bulbs in parallel. You'll make diodes in parallel. You'll make BJTs in parallel, the MOSFETs in parallel, right? So you can have these two in parallel and the combination is in what? A series, right? So the overall current here is going to be 5 by 10 plus 20 parallel with 40. 20 parallel with 40. Sometimes what happens is you might give 2 bulbs like this and 2 bulbs, and you can have a BJT also, right? So you can have a BJT. Then what happens is this bulb is replaced by, suppose you are giving some signal here, a small signal, right? So you are applying a small signal here, 2 sine omega t millivolts. And this voltage by current you will replace by a resistor. by a resistor and the VB by IB. You can put a small signal model here, some resistor here, and this will become a simple problem of 3 resistors. So here the voltage divided by current. So analog engineers, they don't care if it's a bulb or a transistor or a diode. They only talk about, okay, there's a V and there's an I and there's a characteristic. So if you know the relationship between VB by IB, which I will give you, right? The small signal model gives you some R pi here. So you can replace it and you can solve the problem. Okay. So suppose I have 5 volts. There is a 1 kilo ohm resistor and 2 diodes are there, D1 and D2. Okay. Now the respect that we give to a diode is the same respect we give to a bulb. Because we are only interested in the voltage divided by the current. We are only interested in the voltage divided by the current. Suppose the examiner asks you, find I if the diode has a characteristics V1 and I1, which is giving you 0.7 volts. 0.7. So now coordinate geometry is important. The coordinate geometry says that whenever a line is parallel to this is x and this is y and this is some constant k. So whenever a line is parallel to y-axis, the equation is x equal to constant. So you have to look in gate problems. Most of the gate problem, the examiner will give you this x equal. He repeatedly, you see any diode problem, he gives you this. What is this x equal to constant? He says that this diode VD is 0.7 volt. He repeatedly gives. The moment the examiner gives you 0.7, you have to think that, okay, he's giving me a line parallel to what axis? Y-axis. So I can model this device. This device always has a drop of 0.7. So I can replace this device by 0.7. What if the second diode has a different characteristics? The second diode has a characteristics with a slope equal to say 1 by 20. So the examiner has given you 2 diodes. Okay, one diode characteristics has a line parallel to, now this guy is not y equal to mx, he's y equal to mx plus c, mind you. And there is a 0.7 volts here, but then there is a slope of 1 by 20. So how do you solve this problem? How do you solve this problem? If it is a gate problem, then you have to put 5 volts here. And there is a resistance of 1 kilo ohm. And this diode is replaced just by 0.7 because the line is constant. The line is parallel to y-axis. But what about this diode? This diode has also got a slope. So there is a 0.7 in series with 20 ohms. Because the slope is always decided by whom? The resistor, right? So now you can replace the diode also by 0.7. And you can apply a law. That's what I told you. Any complicated problem, the 3 things: define current, voltage, look at the characteristics, and then apply KVL and KCL. This is the same approach for all diode problems, all BJT problems, all MOSFET problems. So you can go clockwise. The good thing about KVL is you can go clockwise, you can go anti-clockwise, same answer. So it's minus 5 plus I into 1K. Or the examiner might put a bulb here, 1 bulb and 2 diodes, right? And he might give you the characteristics of a bulb, which is a resistor, and 2 diodes. So minus 5 plus I into 1K plus 0.7 plus 0.7 plus I into 20. So what is your I? I is going to be 5 minus 1.4 by 1K plus 20. So he has given you two diodes with two different characteristics. Don't always just, the moment you see a problem, don't always take 0.7. When will you take 0.7? Only if the line is parallel to y-axis. How do you know whether the line is parallel to y-axis? See the question. The examiner should give you x equal to constant. The examiner should give you Vd equal to 0.7. So the basic coordinate geometry is very, very important for analog, right? 10 standard, basic 10 standard math, how to characterize a straight line, how to characterize a sine wave. For example, Vm sine omega t, Vm is peak and t is the time period. So these basic mathematics is enough for analog, right? So let us go back here. Any student who wants to start analog, he takes up a device, defines current, voltage, characteristics, have an equivalent model, and he has to know how to apply KVL and KCL. And KCL is fun. KCL is fun. Even if you have a big circuit, you can choose a boundary for that and then take entering equal to leaving, even for a million transistors. So you can apply KCL. But you should know how to take cleverly the element boundaries so that all the entering currents become equal to leaving currents, right? So the effort that you put for a node is the same effort that you put for a million BJT here, right? And don't worry about the time scale. Just think that I'm giving an input, instantly there is an output, okay? So don't worry about the time scale. Okay, so, and what is the other approach which we generally don't do? The other approach is without the model, directly solving it to the characteristic with the graph, right? So the graphical approach we generally avoid. So you can solve with, the graphical approach. This graphical approach is, this is taught to us, in 10th standard, right? So whenever you have a straight line, and the line is characterized by an equation called y equal to mx or y equal to mx plus c, or you can take 2 points and characterize it with x1 y1 and x2 y2. Y minus y1 is m into x minus x1. So graphical approach for straight lines is also quite simple. So if somebody gives you a bulb and say that I am giving a DC voltage of 5 volt. I am giving a AC voltage of say 2 sine t. What is the current? What is the current? So then now you can also solve this problem with graph. How do you solve the problem with graph? The bulb has a characteristics. Suppose if the bulb has a characteristics of, say there is a 2 volt and the current is 0.02. So this is the characteristics of the bulb. When I give 5 volt, we are replacing this bulb by a resistor. If you don't want to do it, if I give 5, what is the current? You can actually choose an operating point here. So you can choose an operating point. If I give 5 volt, this is going to be 0.05. So this approach we will not do, right? Of course, it's quite simple when you have a single bulb. What happens if you have multiple bulbs? Then you cannot superimpose all the graphs. Suppose a differential amplifier is there and it's been biased by a current mirror. A differential amplifier, suppose it has two MOSFETs and it has an active load with another 2 MOSFETs and there's a current mirror also. Then you cannot superimpose 4 graphs on it. So graphical approach we generally avoid it, but in books they show it for a single device. For example, if the bulb has a characteristics like this, it passes through the origin. This is 2 volt, 0.02, minus 2 volt, 0.02. So this is the VI characteristics of the bulb. What happens when you apply 2 sine t? 2 sine t. So when you apply 2 sine t, the easy approach is the model. The model says that the bulb is replaced by 100 ohms. So the current is going to be 2 by 100, 0.02 sine t. So this is easy. This is easy, right? This graphical approach you can avoid. So you can apply the voltage here, which is 2 sin t. So what happens when you apply a signal to a BJT or a MOSFET? So you can superimpose and then take these points. So you can see that when the peak voltage is 2 volt, the current is going to be 0.0. So this graphical method, avoid in exam. Avoid, don't try it, because for one transistor you can do it. But if a couple of transistors are given, every transistor characteristic you cannot superimpose. But you can see how easily we have done a 3 characteristics problem. So you can imagine this is a characteristics of a diode, this is a BJT, this is a MOSFET or something like that. We have replaced all these devices by equivalent circuit and solved. So once again I am repeating, once again, what is the approach to study analog? Don't worry much about the depletion inside, rate of charge buildup inside, doping, P material, N material, nothing. Define current, define voltage, look at the characteristics, experiment, in the lab, somebody gives you this characteristic, try to have an equivalent model and apply KVL and KCL. After applying KVL and KCL, you can nicely calculate all the, problems, gate problems like the voltage and the current. If it's the input voltage, then the V in by I in will be the input resistance. If it's the output voltage, output current, the ratio will become the output resistance. And the ratio of output voltage and output is the voltage gain, current gain. So everything comes from these 2 things. That's what I mean to say. All the gate problems in analog, they come only from these 2, current, voltage, current, voltage. There is no scope for time, thanks to Kirchhoff. And there is nothing called the, depletion, the charge inside, the interaction inside. And we are neglecting the interaction outside the device also, right? But don't put just for fun, don't put a solenoid here and there and spoil the KVL, right? So let's assume that there's no solenoid inside. And because KVL, if d phi by dt is not 0, then the KVL goes wrong, right? So dq by dt is 0, d phi by dt is 0, time scale of input signal is much larger than the propagation delay. So this is how we can solve the gate problems, right? So coming to what we have to remember for exam, that is important. What are the topics we have to remember for exam? For exam purpose, so just now I have given a DC voltage and AC. Mostly in exam, you will have DC and AC. So if you have a resistor of R ohms, then resistor is same both for DC and AC. What is a model of a capacitor? Capacitor is replaced by 1 by omega C. For DC, omega is 0, 1 by 0. 1 by 0 is infinite. You can replace capacitor by open, and for omega, if you consider high, you can replace by short. Inductor. For omega 0, you can replace by short here and open here. And with this simple approach, solve filters in gate problem. Solve filter problems in gate exam. Okay. So whenever resistors are given in the problem, just keep them, right? Respect resistors, because remember, resistor will never change its phase in DC or AC, because V equal to IR, R equal to V by I. And remember, R is same as dV by di. So probably resistor or the bulb is the only component which is same, which is having same values both for DC analysis and AC analysis, right? Capacitor and inductor, completely complementary picture. For low frequency or DC, capacitor will act like open, for AC it is short, inductor for DC it is short, and for AC it is open, right? So you can solve a lot of filter problems very easily with this switch approach. So many gate problems you can solve, right? And then comes the diode. We have just now seen a diode. If the diode is ideal, you can replace again by short, ideal, or you can replace the diode by 0.7 volts. 0.7 volts based on the characteristics. I'll give you the characteristics. So if the characteristics of the bulb or if the characteristics of the diode is right on the y-axis, here the voltage is 0. So whenever you define voltage 0, you can replace the diode by short. Or if the diode characteristics examiner has given like this, piecewise, these are called the piecewise characteristics, but strictly speaking the diode characteristics is nonlinear, but nonlinear it's difficult to solve. You have to apply some nonlinear methods like the Newton-Raphson, and so we are trying to make a compromise between simplicity and accuracy. So examiner himself doesn't care about the nonlinear characteristics, so he gives you piecewise characteristics. And what happens when you apply a AC signal to a diode? When you apply a AC signal or a small signal to a diode, the diode can behave like a bulb. The diode can behave like a bulb. So when you apply small signal, the diode is replaced by a resistance RD equal to eta Vt by Id. Eta is generally 1. So this model, with this model, you can solve lot of gate problems. You can solve half wave rectifier, full wave rectifier problems. You can do peak detector, clampers, clippers, all the problems you can solve. But whenever the examiner applies a small signal, then the diode character changes into a bulb in this regime, in this small rinky-dinky portion of the total characteristics. The diode is going to be modeled like just like a bulb, just like a resistor. So half wave rectifier, full wave rectifier, peak detector, clamper, all the problems you can solve with this simple model. See how simple it is, right? We're not going to think about the interaction inside or the interaction outside. Just replace the device with its equivalent model and solve. And coming to BJT. A BJT is a 3-terminal device, so at least 2 elements are needed. So here, for the BJT to get on, we need 0.7. So the DC model, whenever you want to solve DC analysis of BJT, consider 0.7 volts, or you can just do it here itself, right? Instead of a model, you can just do it here itself, 0.7. And what is IC? IC for a BJT is going to be beta IB or alpha E. IC is going to be beta IB or alpha E. So this, and you can solve all the DC problems, right? So whether there is a voltage divider or an emitter resistor here and there, any problem you can very easily solve just by having 2 things in mind. What is the abstraction in your mind? Don't think about anything about the BJT while solving a gate problem. Think only 2 things. One, at the input there is a 0.7 volts. At the output there is a current flowing which is IC, and IC is beta times of what? IB, or IC is alpha times of IE. Now what happens when you apply a small signal? When you apply a small signal, definitely you will work at a small portion of the characteristics. This is VB, this is say I or IB or IE. You will use only a small portion of the total characteristics. So this VB by IB So BJT is quite simple here. Here this is the delta VB. This is not 0.7 volts. This is the change in that 0.7. You are working at this 0.7. The change in that 0.7 can be modeled as a resistor. The change in VC and IC can be modeled as a resistor. So what is a BJT here? The BJT is hardly a resistor at input and a resistor at output. See how simple is this BJT. So what is a resistor at input side? It is the variation of VB with IB. What is a resistor at output side? It's the variation of VC, small VC by small IC. VC means the change in VC. So this is the characteristics. So you have VC and IC. So you're working only at this portion of the total characteristics. So this line, so now you know why did I take the bulb as an example? Because the effort that you put for a bulb and the effort that you put for a BJT is same. So to me, BJT is also a bulb. The BJT is also just a bulb now, because we are working only at this region of the total characteristics. Right? So as long as you're working at this portion of the characteristic, its behavior is just like a bulb. And of course, BJT is not just two resistors. Its output current is dependent on input. So you can put a dependent source in the model and say it's beta IB or alpha I. So this becomes the model. So if you just take 0.7 volts, you're doing DC analysis. If you take a resistor here, then the resistor value is VB by IB. VB by IB, and some books they call it R pi also. VB by IB. It is beta by GM actually, and where GM is IC DC by 26 millivolt. So if you want to do it numerically, right? So just imagine that there is a resistor here in a BJT, and its numerical value is going to be beta by IC by VT, right? And here you have one more resistor R0, which is the resistance between collector and emitter. This is given numerically as the early voltage by the ICDs. So with this model, you can solve problems like CE amplifier, CB amplifier, CC amplifier, differential amplifier, cascode amplifier, whatever amplifier is there, you can very easily solve with this model, right? But of course, this is for analog. But what about digital? In digital, the same BJT can work in two more regions. One is the cutoff, the other one is the saturation. So in cutoff, whenever the base emitter junction is reverse bias, and suppose you are connecting this to some VCC, which makes this junction also as reverse bias. So in cutoff, the current IC is going to be 0. So cutoff problems are quite simple. All that you have to see is whether this diode is on or not, right? So this diode you can reverse bias in so many ways. You can connect this to ground, this also to ground. So the device will be in cutoff region. Now how do you solve problems in saturation? In saturation, you have to prove that IC is not equal to beta IB. IC equal to beta IB is valid only in the active region, and IC is not equal to beta IB, or more specifically, IB is greater than IC by beta. In saturation, you have to consider VC sat. Examiner will give you this around 0.2 volts. This is 0.7 given by examiner, and you have to prove this. You have to prove that the device is not in active region, right? In active region, you will always see that this VC here Vc is always greater than 0.2 volts. Greater than 0.2 because the 0.2 is the saturation. This regime is called the saturation, and this is the active region. So, okay, if examiner wants you the region of operation, then it's a combination of both analog and digital, because three regions are there: cutoff, saturation and active. But generally, the moment examiner says in an amplifier, he uses the word amplifier, don't check all this, because in analog we build amplifiers. Examiner mentions the word amplifier, think that the device is in what region? Active region. So, the three regions for a BJT is active, cutoff and saturation. So, this is the digital world, this is analog circuits, right. So, you can build analog circuits in active region. So, this is for BJT, right. So, this for a diode, and same thing here. If a diode is reverse bias, you can replace the diode by what switch? Open switch for reverse bias, and in reverse bias you will calculate the voltage Vd, find Vd if a diode is reverse bias. Okay. Yeah, this is the Vc. Here you have Vc. This Vc should be greater than 0.2 for BJTs in what region? Active region. Just treat it like a black box, that's it. Don't go inside the device. Just take 0.7 volts and solve. If your Vc is greater than 0.2, then the device is in what region? Active. Cutoff and saturation. In saturation, your assumption is voltage, your findings are current. In active region, your assumption is current, but your findings are voltage, right. Just find voltage, and whenever you go around the device, just treat this device as a port, that's it, as a port, right. Now, what about MOSFET? If you want to solve MOSFET problems in DC, a MOSFET has three terminals: gate, source and drain. Just think this port as a box and this port as a box. And since the current flowing through MOSFET is 0, MOSFET draws no current. So, it is controlled by voltage. You can replace the MOSFET with an open circuit. And what is ID in a MOSFET? The device equation for a BJT, is IC is beta IB or IC is alpha I. This is given by the manufacturer. So, similarly, the manufacturer's equation. So, here you have VGS. In an open circuit, voltage is manifested, but current is 0, right. So, what is your ID? ID is going to be K times of VGS minus VT whole square by 2. And what is the value K? K is going to be mu Cox W by L. W and L are the width and length. So, this model you can use for all the MOSFET DC analysis problems and you can solve. And pakka on DC analysis problems you will get a guaranteed question in DC analysis as well as in AC analysis. BJT generally of late we are seeing DC analysis of BJT important for electrical students. AC, there are not many questions, right, but the approach for AC analysis in MOSFET and AC analysis in BJT both are same, but we are not seeing questions in this area. In this area, you are getting questions for electrical students, but for EC students, somehow they are avoiding complete BJT topic, because the world is moving towards MOSFETs and IC design. So, no questions of late, last 2-3 years, not many questions on BJT, right? So focus more on MOSFET, and MOSFET is simple because it has only one current, right? So the source current and the drain current both are same because the gate current is 0. So I've shown you KCL. This is I1, this is I2, and this is I3. So I3 is going to be I1 plus I2. So here you can put a MOSFET. You can put a MOSFET. But what happens if one current is 0? If one current is 0, then I3 becomes I2. So all the currents entering is leaving. So this drain current and source current both are same, right? Now for AC analysis, at the input side current is 0, so there's an open circuit. At output side, you have a VDS and ID. VDS and ID, the change in VDS by change in ID is a resistor. So this is VDS by ID, change in VDS by change. You can call it RDS if you want. So this is the small signal model of a MOSFET. But the only difference is these devices are called the dependent sources. They are called dependent. So you cannot just replace them by resistor. You need a dependent source, which is ID is GM times of VGS. ID is GM times of VGS. In BJT, your IC is going to be GM times of VB or beta IB. Anything you can take beta IB or alpha IE or GM VB. There's an option for you, right? But here ID you can take GM VGS. And what is GM? GM is going to be root 2K into ID or K times of VGS minus VT. If examiner gives you this ID, you can calculate GM, or if an examiner give you VGS and VT, you can calculate. In some problems, especially in current mirror problems, no VT is given, but you need GM. So you have to look for this formula, right? If he gives VT, fair enough. Right? So what is RDS again? RDS again is going to be early voltage by IDDC. But sometimes in some books, 1 by early voltage is given by some factor called the lambda, right? But right now, if you ask me, how do I know whether this is this? Use some basic common sense. The units of VA is volt. The unit of lambda is per volt, 1 by volt. So if he gives volt, substitute here. If he gives per volt, substitute here, right? So this is the AC model and this is the DC model. And for digital, for analog, this device works in saturation, not in active. We don't say active here, we say saturation. But for digital MOSFET, you have a cutoff and ohmic region or triode. So when do you say that a MOSFET is in cutoff? For a MOSFET to be on, this VGS, if it is less than VT, then the ID is treated as 0. So it is in cutoff region. And when do you say that a MOSFET is in triode or ohmic region? Is this is VGS and VDS. If this voltage shrinks, then it becomes a digital circuit, something like an on switch. If your VDS is less than VGS minus VT, then they can use it for digital, right? For analog, we use MOSFET in saturation region. In saturation, as we want a larger output swing, this VDS should be greater than VGS minus VT. VT being the threshold voltage. VT being the threshold voltage. So MOSFET, just like the BJT, it has 3 regions. 2 regions are for the digital, 1 for analog, right? And what is the current equation in a triode region? ID is K times of VGS minus VT into VDS minus VDS square by 2. But for saturation, ID is K times of whole square by 2. So just go through this.